My name is Aydin Abadi. In this talk, I'll present multi-instance, publicly verifiable TimeLock Puzzle and its applications. It's a joint work with Professor Aggelos Kiayias. TimeLock puzzles are interesting cryptographic primitives that allow sending information to the future. They enable a party to lock a message such that no one else can unlock it until a certain time has passed. Time-lock puzzle protocols can be categorized into two categories. Category 1, those that use an assistance of a trusted third party to support time release of a secret. This category is not our focus in this work. Category 2, those that do not involve a third party. The latter category is the focus of our work. In time-lock puzzle protocols, the party who wants to unlock the message does not need to know the secret key to unlock a locked message. Instead, as soon as it receives the locked message, it continuously works on it until it unlocks the message. The amount of time that requires to unlock a message is fixed and known ahead of time. The time-lock puzzles that do not involve a third party are often based on sequential squaring. They are believed to be secure against a solver who may have access to many computation resources that run in parallel. In general, there are two parties involved in a time-lock puzzle protocol, a client and a server, or solver. In the protocol, first the client encodes a message into a puzzle such that it should be revealed after a fixed time. Then it sends the puzzle P1 to the solver. Upon receiving the puzzle, the solver works continuously on the puzzle until it finds the solution after a certain time. Time-lock puzzles have numerous applications, such as fair contract signing, e-voting, release of confidential documents over time, and sealed bid auctions. Over the last 2 decades, a variety of time-lock puzzle protocols have been proposed. However, the existing schemes are not suitable for the case where a solver is given multiple instances of a puzzle at once and it must unlock them at different points in time. Note that the multiple instances puzzle is a natural generalization of the single puzzle setting. If the existing schemes are naively used in the multi-puzzle setting, then the solver has to start solving all puzzles as soon as it receives them in order to find each solution on time. This ultimately imposes significant computation costs and demands a high level of parallelization. Let's have a closer look at the problem. Consider the case where a client wants a solver to learn a vector of messages M1 to MZ at times F1 to FZ respectively, where the client is available and online only at an earlier time, say F0 smaller than F1. A naive way to generate multiple puzzles is that the client uses one of the existing time-lock puzzle schemes to encode each message MJ separately, such that it can be decoded at time fj if all puzzles and public keys are passed onto the server at time t0. For the solver to decrypt the message on time, it needs to start decrypting all of them as soon as the puzzles and public keys are given to it. The above naive approach yields two serious issues, demanding a high level of parallelization as each puzzle has to be dealt with separately in parallel to the rest, and imposing a high computation cost as the solver has to perform very high number of squaring to decrypt all messages. As can be seen, the total number of required squaring is significantly high. To address the issues, we put forth and formally define a primitive called MultiInstance TimeLock Puzzle, which allows composing a puzzle's instances. In this scheme, given the composition, a solver can deal with each instance sequentially. Moreover, we present an instantiation of the primitive. The instantiation is called Chained TimeLock Puzzle, or CTLP. The Chained TimeLock Puzzle makes black box use of a standard TimeLock puzzle scheme. Therefore, the core traditional TimeLock puzzle remains unchanged in our protocol. The chained TimeLock puzzle has a lightweight and efficient verification algorithm. The verification algorithm imposes very low computation and communication costs to the parties. Furthermore, the verification algorithm allows anyone to check the correctness of a solution found by the solver. Thus, it supports public verifiability. The chained TimeLock puzzle's overall computation complexity of solving Z puzzles is equivalent to the computation complexity of solving only the last puzzle. Also, solving puzzles imposes communication costs linear with the total number of puzzles, Z. So its communication complexity is O of Z. Our chained TimeLock puzzle scheme is the first TimeLock puzzle protocol that offers all the aforementioned features. Our key observation is in a naive approach, the process of decrypting messages have many overlaps, leading to a high computation cost. So by eliminating the overlaps, we can considerably lower the overall cost, both in the puzzle solving and puzzle creating phases. One of our core ideas is to chain the puzzles. While chaining different puzzles may seem a relatively obvious approach to tackle the issues, designing a secure protocol that also makes black box use of a standard TimeLock puzzle scheme can support public verifiability and can have low costs is challenging. At a high level, in our solution, the client first encrypts the message, say MZ, that is supposed to be decrypted after the rest, say MZ-1. Then the client embeds the information needed for decrypting that message, i.e. MZ, into the puzzle of the message that will be decrypted before that message, i.e. mz-1. In other words, the client integrates the information needed to decrypt message mj into the puzzle related to message mj-1. Therefore, the puzzles are chained with each other. Let's have a closer look. Recall that the client has a set of messages M1 up to MZ, where M1 is supposed to be discovered at time F1, M2 is supposed to be discovered at time M2, and finally MZ is supposed to be discovered at time FZ. To generate chained puzzles, the client starts from the last message MZ. It processes MZ to generate a puzzle PZ. During this process, it also computes a public key PKZ for that puzzle. Then the client moves on to the next message MZ-1 that is supposed to be discovered by the solver before MZ. It processes MZ-1 to generate a puzzle PZ-1. However, it embeds the public key for MZ into puzzle PZ-1. During the process, it also computes a public key PKZ-1 for puzzle PZ-1. It repeats the process until it reaches to message M1. It processes M1 to generate a puzzle P1. However, it embeds the public key PK2 for message M2 into puzzle P1. During the process, it also computes a public key PK1 for puzzle P1. It publishes all puzzles P1 to PZ along with public key for puzzle 1, which is PK1. By the end of this process, the client created a set of puzzles that are chained with each other. Recall that the solver is given Z puzzles P1 up to PZ along with PK1, which is the public key for the first puzzle. In order for the solver to solve the puzzles, it has to start from the first puzzle P1, which is the opposite direction that the puzzles were created. Given PK1 and P1, the solver performs sequential squaring until it discovers message M1 and PK2, where PK2 is the public key for the next message. After that, the solver moves on to the next puzzle P2. It uses PK2 to perform sequential squaring to solve the puzzle. It discovers message M2 and PK3, where PK3 is a public key for the next message. The solver repeats the process until it reaches to the last puzzle PZ. Given the last puzzle and the related public key PKZ, which was discovered from the previous puzzle, the solver performs sequential squaring until it discovers the last message, MZ. By the end of this process, the solver finds all puzzle's solutions, M1, M2, up to MZ. As can be seen, our scheme requires fewer exponentiations than the naive approach would require. Therefore, our scheme imposes lower costs. As I mentioned previously, the chained TimeLock puzzle supports public verifiability. To let the scheme support efficient public verifiability, we use the following technique. When the client generates a puzzle for a message, it uses a commitment scheme to commit to that message as well. The client embeds the commitment's opening into the puzzle for that message. Then the client publishes the commitment for every message, so the public can access it. Also, the client sends the puzzles to the solver. Due to hiding property of the commitment, nothing about the message is leaked to the public or to the solver. Usually, in commitment schemes, the client who initially commits to a value later on opens the commitment. However, in our scheme, the client does not open the commitment itself. Instead, the solver opens the commitment after it finds the solutions. In particular, after the solver finds a solution, it decodes the solution to find the opening and send it to the public. In this case, given the opening and the commitment, anyone can check whether the commitment matches the opening. In our protocol, any efficient commitment scheme can be used, such as hash-based scheme, which is in the random oracle model. This commitment is highly efficient. Or Pedersen scheme in the standard model. This commitment scheme is less efficient than the hash-based one as it involves modular exponentiation. However, it is in the standard model. Our protocol has various applications, such as mass release of confidential documents over time, gradually revealing multiple secret keys, verifying continuous availability of cloud services such as data storage or secure hardware, scheduled private payments, where not only is every payment made after a predefined period, but also the payment's details remain hidden during the period. In this work, we showed concrete applications of our chained TimeLock puzzle and demonstrated its use case in a blockchain-based solution. In particular, we combined the chain TimeLock puzzle with a smart contract. We applied the combination to outsourced proofs of retrievability research line and proposed a smarter outsourced proofs of retrievability scheme. Our scheme offers a combination of real-time detection and fair payment properties, where real-time detection means a data owner or client is notified in almost real time when a proof is rejected. While fair payment means in every verification, the storage server is paid if and only if a proof is accepted. Our scheme imposes very low overhead. A combination of the above features makes our scheme very suitable for mission critical data. As another application of the chained TimeLock puzzle, we illustrated that in certain cases, one can substitute a verifiable delay function with a chain TimeLock puzzle to gain much better efficiency. Specifically, using the chain TimeLock puzzle, a prover's computation cost will be reduced by factors of 3, and its communication costs will be reduced by a factor of 6.5. We reached to the end of this presentation. I hope you enjoyed.